Okay, welcome to lecture. We'll get started here in just a second. We're continuing on chapter 4, I think. We're going to finish up chapter 4 and then probably go to chapter 5. Those notes, again, can be found online on our Canvas site if you need chapter 5 notes. And again, we'll get started here in just a second. Just let everybody in here. Okay, so we been talking in chapter 4 here. We in the previous chapter talked about Lewis structures and obviously drawing Lewis structures. We talked a little bit about bond polarity as well. And then we got into some molecular geometries, electron pair geometries here in this chapter at the beginning. So a lot of those you might be familiar with. There was a lot of probably new geometries for you, and most of them are set around those expanded octets that we've been talking about. Again, those guys that could go 5 electron pairs, 6 electron pairs. And again, there's a lot of geometries that go with that. So again, triangular biparameter, which is our 5 electron pairs. And there's again a set of guys that had some non-bonding electrons that were in there. Things like seesaw and T-shaped and those type of geometries. Then we also had, when we get to 6 electron pairs, sort of the base of 6 electron pairs being our octahedral geometry. And again, there was those guys with non-bonding electrons, which obviously has some different geometry names in terms of their shape. Things like square planar, square pyramidal. So, we got a lot of those kind of new geometries that go with it. Remember that when you do geometry, as we talked about, basically you want to draw your Lewis structure. You want to make sure the important thing when you do geometry is the central atom. So you want to count up how many electron pairs are around that central atom. Again, it doesn't matter if it is bonding electrons, non-bonding electrons, it's just total electron pairs around the central atom. The one major thing that you want to keep in mind when you're doing geometry, and really only sort of when you're doing geometry sort of things, is that if you did draw a Lewis structure that contained a double bond or a triple bond, when you go around to count them, it counts really as only 1 electron pair and 1 bond as well. So that's the major really thing to keep in mind as you're doing geometry. Again, triple bonds, double bonds count both as only 1 electron pair and also 1 bond as well. We then got into the idea of hybridization, which is sort of a theory of modeling, theory of bonding, I guess is a better way of saying that. There's a theory of bonding that helps us sort of understand why we see certain bond angles associated with molecules. And again, a hybrid orbitals are when we take our atomic orbitals. So again, a reminder that when we talk about atomic orbitals, we're talking about our S's, our P's, our D's, our F's, right? And when we combine these guys, and again, as we talked about, really sort of the easiest way to apply hybridization is to kind of think about sort of the order at which these atomic orbitals kind of are. And when you're trying to apply hybridization, you always kind of start down here. And it is based off of really electron pairs. So the hybridization is really based off of the electron pair geometry. And that means, again, here, when you're doing hybridization or counting electron pairs for hybridization, you also want to count double bonds and triple bonds is just one electron pair. So again, here, in addition to sort of the geometry and stuff that we were doing before with hybridization, you do want to kind of go around and count everybody almost like you were doing geometry, and then sort of apply your hybridization. And basically, when we mix some of these orbitals, these atomic orbitals, so for example, if we took an s orbital and a p orbital and we mix them, we will get two sp hybridized orbitals. We will also get two unhybridized p orbitals that do not go through hybridization. So the total number of hybrid orbitals that you will make will be equal to the number of, the number of atomic orbitals that you've put together. So in this case, we took one s and one p and we put it together, and we get two hybrid orbitals out of that. And again, really the simplest way to sort of apply things is really just looking at that atom. And again, if we look at this carbon here, it's got 1, 2, 3, 4 electron pairs. And again, you can just start here and go 1, 2, 3, 4. That's an S and 3 Ps. That means this will be sp3. It really is as almost simple as that, is the way you can identify hybridization. Is you literally can almost just count off basically what you got going on. So we can apply hybridization to the central atom. We can also apply hybridization to the outside atom. Something, for example, like hydrogen that has only one electron and one orbital will not go through hybridization, but pretty much most everything else will or could go through hybridization, and you could apply hybridization to that. We also saw that, there's sort of a way to classify bonds as well. And, we sort of have, when we draw things, a single bond, which is like one line. We have a double bond, which is like 2 lines. And we have a triple bond, which is obviously 3 lines. So really, all single bonds for the most part are what are referred to as sigma bonds. And really, sort of the definition of a sigma bond is sort of how those orbitals come together. They basically come together head on, so they just go right into each other. And there's an area where there's overlapping that occurs, and that's basically what creates a sigma bond. And that, sort of practical aspect purposes of it is, kind of the first line that you draw. So all the first lines that you draw, including in a double bond, that first line would also be a sigma bond. That first line that you draw for a triple would also be a sigma bond that's there. Now, to make sort of the second line, if you will, and the third line there for our double and triple bonds, those are what are referred to as pi bonds. So let's grab a different color here. So this guy here, kind of that second line, the second line here, and I just kind of erased it there by accident, but the third line as well. These are what are known as pi bonds. And pi bonds are really these guys here. These are the unhybridized p orbitals. And again, these unhybridized p orbitals will look like regular p orbitals. Remember that the hybrid orbitals kind of change shape, and they also have the same energy. But our unhybridized p orbitals, they overlap what are sometimes referred to as sideways. So there's sideways overlap that happens with these p orbitals, and that's what creates that double bond. And then obviously one more set of p orbitals could make a triple bond by doing the same sort of overlap. So the major difference between sort of a pi bond and a sigma bond, again, the orbitals come head on to each other and overlap. Sideways overlap between those unhybridized p orbitals is usually what we have for our p orbitals and our double and triple bonds. Any questions on that there? Just trying to think where I want to go here. Okay, so let's just talk a little bit about one more sort of aspect of this and sort of hybridization and sort of our double bond, triple bond, and our pi bonding that's occurring and how that occurs. So what I'm going to do, I think, kind of clear my screen here, I think. Okay. So let's say we took, for example, this guy here. So when we look at this guy here, we obviously have two central atoms. We have two carbons. They're double bonded. And what we could see here, if we want to do hybridization, so I'll let you decide here, take a second and think of what the hybridization of each of those carbons are. And we'll see if you are right on that. So hopefully you should have came up with sp2 hybridization on both of those carbons. Again, if we count the electron pairs, one electron pair there, two electron pairs there, double bond counts as only one. So 1, 2, 3 electron pairs. Again, if you were kind of working your way up this thing, 1, 2, and 3, sp2. Yeah, same thing on the right-hand side. We have one electron pair, two electron pairs. Again, double bond becomes 3 electron pairs. And again, if you sort of did your counting, an s and two p's give you your sp hybrid orbitals. So let's just talk about a little bit about the arrows and sort of showing you kind of where everybody ends up here. So if you remember, if we go to the periodic table, got one of those here, go. Carbon is number 6, which means that it would be 1s2, 2s2, 2p2 for carbon, right? And obviously this would be its valence electrons there in group number 4, as we see. And if we were to sort of follow that hybridization process like we saw before, this would be our 2s. It would have that. And be a really badly drawn 2p. It would go like this. So as this would go through hybridization, as we talked about last time, this electron in the lower guy would come up to this empty spot here. And then it would hybridize, right? So we would get this guy that would go, looks like this. And each of these would have an electron in it. And since it is going to hybridize as sp2, that means we're going to take this guy and those two. Now, since we hybridize 1, 2, 3 atomic orbitals, what that should give us is 3 equal in energy, equal in shape, as I draw it really badly, sp2 hybrid orbitals. They each should have an electron in it. We will also have this guy here, which is unhybridized. So we will have that p orbital. That is just a regular p orbital that's unhybridized and still have an electron in it. Now, I'm going to call this guy carbon 1. So this is for carbon 1. Now, carbon 2 is identical to that. So for carbon 2, it's going to do an identical type of situation. It's going to have its 3 sp2 hybrid orbitals, each with an electron in it. It will also have its unhybridized p orbital here. So when this goes through hybridization, this is essentially what you're going to have. And again, this is just to illustrate sort of, where all the bonds come from, how we get all those bonds. So let me just grab a different color here, maybe. Go reddish. Now, We also have, if we look, right, 1, 2, 3, and 4 just hydrogens, right? Just regular hydrogens. So I'm just going to kind of draw them almost like the picture is. We have a hydrogen over here. It has a 1 electron in its 1s. We have a hydrogen over here. Also has 1 electron in its 1s. We have a hydrogen over here. Has an electron in its 1s. And we'll just throw this hydrogen up here. Electron in its 1s. So those represent obviously the 4 hydrogens that we have. Again, hydrogen will not go through hybridization. It just has that 1 electron. That 1 electron is in the 1s orbital, again, from the electron configuration, right, of hydrogen. 1s1, right? So that's the electron that we're talking about here. This guy right here is this electron in each of those. So when we start to make the bonds, so let's take a look at the bonds and just kind of see how all these guys come together and how it explains everything. We're going to start right here with this bond. So this is the bond between the carbon and the hydrogen. So for example, this sp2 from that carbon will go and bond with that hydrogen there. They would obviously be sharing those electrons, and that would account for that bond that we just saw there that we called number 1. That would be a sigma bond right between the carbon and the hydrogen, right? So that would be a sigma bond, which means the sp2 orbital in the carbon and the 1s orbital will basically come straight at each other head on and make that sigma bond. We also have an exact same type of bond happening here between the carbon and the hydrogen. So let's just say, for example, this orbital here, this sp2, will come and bond with this guy. And that would also make a sigma bond as well and accounts for that second bond that we see there. With also an sp2 in carbon number 1 and a 1s orbital in the hydrogen. We have identical bonds on the other side on carbon number 2. I didn't label it. We'll call this carbon number 2. So this bond here between a carbon and the hydrogen, same idea. Going to bond here, even though I missed it there. That's going to be number 3. Also going to be a sigma bond, right? This guy here to here would be the 4th carbon hydrogen bond that would occur. Say this guy here. And now if you just kind of look at a couple of things that we got going on in terms of the carbons on the bottom, we have now used all of the carbons, sp2 hybrid orbitals, except for 1 hybrid orbital on each of the carbons to make each of those sigma bonds. So there's only 2 bonds that we have left really to sort of account for in that molecule. And if we look at it, we have the double bond right in the center. It's the last 2 that we have to account for. So the first line in that double bond, we'll call it number 5, is between the carbon sp2 orbital and the carbon sp2 orbital on the other side. And that would be number 5, which would now be, again, a sigma bond at this case. So the very last bond that's there is this second bond here for the double bond, number 6. And you can see the only electrons that we have are now these unhybridized p orbitals. And that is what's going to actually make our pi bond in this case, number 6. It's these unhybridized p orbitals. Again, the difference between these sp2 sort of coming together and these is when these guys come together, again, since they are unhybridized, this is where we get that sideways overlap that's going to make that double bond that's going to occur. So you can see that you could kind of use hybridization again to describe sort of what's happening. You can see it nicely shows you where all the electrons really go to. If you get this detailed, you won't be asked to draw anything like that. But again, this is just hopefully to kind of show you sort of where the electrons go, how they sort of come together, and how they make all those bonds in that case. And as you can see, because those are the unhybridized p orbitals, that's how they're going to overlap, is that sideways overlap, and that's going to create that type of bond, which again is that pi bond that's going to occur. Any questions on any of that there? And again, like I said, you won't have to draw the boxes, the arrows showing how all the bonds come together. It is just hopefully to help you maybe visualize sort of how these electrons are coming together. You will have to do like what we did yesterday and a little bit here today is, again, if you draw the Lewis structure or a Lewis structure is given to you, you need to be able to identify the hybridization of the atom and also obviously how many sigma bonds, pi bonds, all that. Yeah, so just to make sure I know, which are you talking about this guy here, or is that the figure? Yeah, okay. Yeah, so when we talk about sort of these orbitals, these are really maybe badly drawn, but if you remember, p orbitals look like these figure eights, right? There's 3 different types of p orbitals, right? And they all kind of look figure eights here. And that's different than, these are just a regular old atomic p orbital. Just like an s orbital, it's essentially, you know, just a sphere and stuff like that. So when we get to the pi bonds for our double bond and our triple bond, they will always be a result of just these regular old p orbitals. They're not hybridized or unhybridized, so they kind of look like that figure 8. So the overlapping that occurs with our p orbitals when they make these pi bonds is what is referred to as sideways overlap. So I'll just kind of draw a line here in the middle. This is sort of where you can imagine like the atoms are and the plane of the bond is like right there. So kind of above and below where kind of those bonds is being made, these unhybridized p orbitals will basically overlap sideways. And again, in the middle, you could kind of imagine here is where the actual true atoms are bonded together. But these p orbitals sort of stick up above it and they overlap kind of sideways like that. And that's maybe a better picture down here without that third line in it. But it's that sideways overlap that occurs. And that's different than what is known as like a sigma bond. And a sigma bond, we'll just kind of use these guys here. In a sigma bond, what happens is they basically run right into each other and they overlap what is referred to as head-on overlap, where those 2 orbitals basically come right together. So I think maybe actually I have a better picture here. Maybe I think we had one. Oops. Where is that? So this is an example of like a sigma bond. So again, here you have the 2 orbitals, and basically they run straight at each other, and you get this area of kind of where they overlap with each other, kind of right onto each other, and that's these kind of bright areas here, kind of like the nucleus in each. And you could kind of see that there's this overlapping area, almost like they just ran straight into each other and kind of blurred together. And that's what happens in a sigma bond when they come straight at each other. Now in a, I should have that picture coming up next, I think. In a pi bond, we get this sort of situation here. And what happens is, again, these are kind of like your figure eights type of thing for p orbitals. And when these come together, they come together sideways, and kind of that merging occurs above and below the plane of where the bond is happening. So this little dot here and dot here is sort of where all the bonding's happening. And those orbitals, again, will kind of overlap above and below. And they overlap above and below sort of the plane of the bond because it's a p orbital. So they got like a lobe over here, right, above and below where the bond's happening. So when they come together, they sort of squish together that way, like above it and below, kind of encasing the bond. And that's what makes that double bond. And then another set of p orbitals can do the same thing and make that triple bond. So it's sort of a different way that those orbitals overlap when they come together. And that's essentially how unhybridized p orbitals will always overlap. They'll come together above and below that plane. And that's different than a sigma bond where it basically straight on and then they kind of blurb together and make that blob. Other questions on that? Now, to make like a triple bond, for example, and I'm going to do a really bad drawing here. So, for example, if we had a triple bond, you would have, again, one set of p orbitals that would be overlapping like this. And then you would actually have another set of p orbitals. Remember, they're on different, like x, y, that are also overlapping. And that's sort of goodish. And you really have that situation happening when you have a triple bond, is you actually have two sets of p orbitals. That's a total of 4 unhybridized p orbitals that will basically come together to make that triple bond. First a double bond and the triple bond. So maybe, let's see here, I can kind of show that here. So for example, if we had this, and again, if we applied the hybridization to this guy, 1 electron pair, triple bond only counts as 1. So this is sp hybridization. And same thing here, this is going to be sp hybridization. So when S and P come together for each of those carbons, we'll call it carbon 1, carbon 2. For carbon 1, what we're going to get is 2 sp hybrid orbitals and 2 unhybridized p orbitals, each have an electron in it. And over here on carbon number 2, we will get the same thing that will occur. We'll get 2 sp hybrid orbitals and 2 unhybridized p orbitals over here. And again, if you just kind of count your bonds, this would be bond 1. So this would go to the hydrogen for bond 1. On this carbon, same thing, bond number 2. Now we also have here a triple bond at this case. Again, the first line in our triple bond would be between these two guys. So that's an sp and an sp in the carbons. Then we have the second and the third guys coming together. And again, we would have this for our first pi bond happening. And then our second unhybridized would make our second pi bond that would occur, which again would be like your double bond and your triple bond. So when you have something like a triple bond, it will hybridize as sp, which will leave 2 unhybridized p orbitals. And those 2 unhybridized p orbitals is what's available to make like that triple bond that we see here in this particular picture. And you could get even super specific about as to what unhybridized orbital you're talking about, because if you remember, this guy represents the px orbital, right? Py and pz. So when you have just one unhybridized p orbital, is the pz orbital. When you have 2 like we have here, it's actually the py orbital that gets part of the triple bond. So we won't get that specific about it, but you can get to the point where you could pretty much go, this is a bond between this orbital and this orbital, and it's a sigma bond or a pi bond between these two things. You could get really that specific. And again, we won't get really, I don't think that specific here, but you should have sort of an understanding of sort of how these guys come together. Any questions on any of that hybridization involving pi bonds or any of that type of stuff? Again, a reminder, you won't be asked to draw the pictures like I just did here, you know, so you won't be asked to draw the, you know, this type of stuff here. But again, you will need to be able to identify the hybridization and also obviously sigma and pi bonds. And again, these pictures of the arrows are here just to hopefully help you visualize sort of how everybody's coming together and where the electrons sort of end up. Any questions on any of that? That should be that, I think. All right. All right. So the last thing we're going to talk about here in terms of bonding is molecular polarity. And we already talked a little bit about polarity before. So just a reminder that what we talked about before, what is sometimes referred to as bond polarity. And bond polarity is really just that. It is typically what we use that difference in electronegativity values for. And usually when we look at the difference in electronegativity values, we're simply looking at an individual bond between two things like this, and using that difference in electronegativity values to determine whether or not, again, that bond is polar, non-polar, or even ionic. And remember, if we do have a polar bond, if we do have a polar bond, we could represent it with that arrow, where again, it points to the more negative side of the bond, so the more electronegative part of the bond, and the one that kind of makes a plus at the end there on the left to the more positive side of the bond, so the one that's least electronegative when we look at it. So bond polarity is not necessarily the same as molecular polarity, which is what we're focusing in on here. Now, in certain cases, it may be the same, and we're going to talk about in what situation is sort of the same situation. But typically speaking, they are two different sort of things. So bond polarity, typically electronegativity differences, that 0 to 4 numbers are just a general trend on the periodic table. And again, that just usually specifically for that individual bond tells you whether or not it is a polar or non-polar type bond. When we talk about molecular polarity, which we're talking about here, that's the entire molecule as a whole. So that's looking at the entire molecule. It's looking at all the bonds that there are in that entire molecule and deciding in an entire molecule, the entire thing, is there an overall separation of charge, which means overall taking every bond into consideration, is there a side of that molecule that is more negative? And is there a side that is more positive? Are they overall sharing the electrons equally? So if we do get that situation where basically there's like a positive side to the molecule or the negative side to the molecule, that is what is known basically as a polar molecule. And all polar molecules will have a dipole moment. So these guys will have what is referred to as a dipole moment. And oddly enough, the dipole moment is represented with the same type of arrow that we used before. So in this particular case, we would draw that arrow heading towards the negative side, and that would be our dipole moment. So polar molecules have a dipole moment, and basically could be really small, could be a large sort of difference, but basically some type of difference in terms of the positive and negative. Obviously, that is different than if we find out everybody's going to kind of equally share the electrons as a whole. That this would be like a nonpolar molecule. And a nonpolar molecule does not have a dipole moment, so you wouldn't draw any arrows for it. For a lack of a better sort of description, it's thought of as being pretty much like neutrals. So everybody as a whole with all the bonds, they're sharing those electrons relatively equal to each other. So what that means is there's no real positive side of that molecule. There's no negative side of that molecule. We're not going to obviously calculate dipole moments or anything like that, but just in case you wanted to, that's kind of how you would do it. But we were not going to get into that obviously here. Okay. So if your molecule ends up having a dipole moment, it's a polar molecule. If it has no dipole moment, then it is a non-polar molecule. So let's talk about really probably the easiest ones to determine whether or not something is polar or non-polar in terms of molecular polarity. And those are our diatomic molecules. Now, our diatomic molecules, as you may know, are basically molecules that contain two atoms only. And there's basically two types of diatomic molecules. There's homonuclear and heteronuclear. So just like homogeneous and heterogeneous type mixtures, homonuclear means that they are the same element involved, and heteronuclear means that they have different elements involved. So if we look at something, for example, like F2 that we saw earlier, now if we look at something like F2 and we look at the bond that's there right here in the middle, Obviously, if we did our electronegativity difference, since they both have the exact same electronegativity, that is going to give us a 0 in terms of electronegativity for that bond that we see here. And that bond that we see here is going to have a 0 electronegativity, which tells us that it is a nonpolar bond. Now, that is the bond polarity for this molecule. But because this is a diatomic molecule, it only contains one bond total, which means the only bond in the entire molecule there is nonpolar, which means by default, this guy also needs to be a nonpolar molecule. So anytime you have a diatomic molecule, and pretty much it's the same guy on each side, you know, regardless if it's single bonded, double bonded, you know, whatever it may be, triple bonded. These are all going to be nonpolar molecules. And that's because in each of those, they each contain only one bond, and that bond is nonpolar, which means the entire molecule in that case has to be nonpolar. So pretty simple. If you got two of the same diatomic molecule, pretty much I wouldn't think about it very long. Just write nonpolar molecule. The molecular polarity should be nonpolar. Again, because only has one bond, that one bond is nonpolar. It's got to be a nonpolar molecule. Now, if you look at something where we have two different molecules, or atoms, or elements, I guess, we'll get that right word there. We know that when we do take the difference in electronegativity here, it's something like 4 and 2.1, so like 1.9 difference. We know that this bond is a polar bond, right? Heading towards the fluorine. So this is a polar bond. Again, the difference in electronegativity is something like 1.9 when you do it. Now, for the exact same logic that we were just talking about above, because this is a diatomic molecule and that is the only bond that we see in the entire thing, and that only bond is polar, we know that this guy is also a polar molecule. And this arrow would represent both the bond dipole and also the dipole moment. Again, the fluorine would be more negative, as it's pointing that way, it's more electronegative, and the hydrogen side there would be more positive. So the H side more positive, the fluorine side more negative. Same thing again, if you had HCl, again, it would have a polar bond heading in this direction. And because this is the only guy and the only bond in that entire thing, that would represent its dipole moment, and this would be a polar molecule. So the super easiest ones to figure out in terms of molecular polarity is your diatomic molecules. Again, the very simple rule is if you have a nonpolar bond, the molecule will be nonpolar because it's the only bond that's there. And if you determine that that bond is polar in a diatomic molecule, the molecule will also be polar because it is the only bond that is present. Any questions on molecular polarity with diatomic molecules? So really, the diatomic molecules is really the only place, for the most part, where you can probably safely say, I know the bond is polar, then the molecule is polar. Or the bond is nonpolar, the molecule will be nonpolar. And again, that's simply because that's the only bond in the whole thing. Now, if everything was that simple, that would be great, but unfortunately it is not. So when we get into molecules that have 3 or more atoms involved, you have to look at actually a couple of different things to determine whether or not the molecule is going to be polar or nonpolar. And let's see what we got there. So when we have 3 or more atoms involved, you really need to look at two major things. First off, are there polar bonds? So again, here you would use that difference in electronegativity or just the general trend of electronegativity on the periodic table to help you decide whether or not those guys are going to be polar bonds or non-polar bonds. And second thing that you have to look at is the molecular geometry. So not the electron pair geometry, but the molecular geometry or the shape of the molecule. So you have to look at those two things when you're trying to determine, is a molecule going to be polar or non-polar? You have to first see, is there polar bonds? And again, if there are polar bonds, the geometry of it. So let's take a look here, for example. Let's take a look at this guy. Let's take a look at CO2. So CO2, when we look between the carbon and the oxygen, we know that the carbon and the oxygen is a polar bond. And we know that because we look on the periodic table, carbon and oxygen are hanging out there in the same period. And oxygen is further to the right on the periodic table. And that means that oxygen is more electronegative. So it does have polar bonds. So if we drew those like dipole arrows, it would be heading towards the oxygen there. It would also be heading towards the oxygen there. So this guy, for the first sort of thing that you need to look at, does have polar bonds. So you may say to yourself, well, it makes sense. It's got polar bonds, so probably going to be a polar molecule. And you wouldn't be a little incorrect in that, because the second thing that you have to look at is the molecular geometry or the shape of it, which is again the molecular geometry. And if we look at this, central atom has one electron pair on the left, two electron pairs on the right, and one bond and two bonds. So if you remember, two electron pairs and two bonds is going to give us a geometry basically known as linear. So the geometry here is linear. You have these dipoles heading in each direction. So for example, if I do this here, if I pull on my pin this way, because the oxygen is pulling this way, and my other oxygen is pulling this way, and I actually just pull really hard, believe it or not, I'm actually pulling extremely hard on both sides of my pin here. And hopefully you can see that my pin is going nowhere, right? Because we have equal guys pulling on opposite sides, and they essentially will cancel each other out. So these dipole arrows that we draw here, they're really what are referred to as vectors, right? And physics, right? Vectors have direction, they have magnitude, and then I fell asleep in physics and don't remember the rest of that. But I do woke up enough to remember that in certain cases, these vectors can add to each other. And in certain cases, these sort of vectors will cancel each other out. And this would be a case where they would cancel each other out. So typically vectors will cancel each other out whenever they're heading equal and opposite of each other, or if they're kind of heading like straight on to each other, they will sort of cancel each other out if they're kind of equal and heading straight on to each other. So CO2 is a very good example of, you could definitely have a molecule that has polar bonds like it does here. So it's got a polar bond between the carbon and the oxygen, the other carbon and the oxygen. But because of the molecular geometry here, they will actually cancel their contributions out. And CO2 is actually a non-polar molecule because of that. So again, a very good example to illustrate that definitely can have polar bonds, but you do need to check the geometry to see whether or not those guys will sort of cancel each other out or sort of add to each other. Sometimes people think about it like a rope, like people, if you're kind of pulling equal at each other, you know, you're gonna, the little flag is not gonna move anywhere. If you're kind of doing tug of war, right, it's gonna kind of stay in the middle. Also, pushing works the same. So like two people on opposite sides of the door pushing equally, right? The door is not going to open one way or the other. If you have like a swinging door, right? Both kind of push equally. They're going to kind of cancel out their contributions. And that's sort of what you want to visualize as you're looking at these things. So for example, let's take a look at our H2O, right? So when we draw our H2O, our water here also contains polar bonds, right? It has the hydrogen, the oxygen, again, the electronegativity difference. Oxygen going to be more electronegative, which means if we were drawing those dipole arrows, they would head towards the oxygen in each case. Now, just like over here, this guy does have polar bonds. So we do want to look at the molecular geometry here to see whether or not this is going to be a polar molecule or not. And if we look at this, this again is 1, 2, 3, 4 electron pairs and 2 bonds. So that is a geometry of bent or V-shaped. So if you visualize sort of what's happening here in this molecule, you got something like this, and everybody's kind of coming up here towards the top. You could almost imagine at the top, if you're pulling a rope, you could kind of pull it and imagine the whole molecule would probably move with it. And this actually would be a polar molecule. And that's because those vectors or those dipole bond dipoles, they're not going to cancel each other out. So I'm going to attempt my really bad physics here. So if we drew our first vector, just in case, they do add to each other. And you drew your second vector, you typically do like a head to tail type of thing. That was a very badly straight line. And basically in this case, they will add to each other and we will get a net dipole moment heading in this direction. I overshot it there. So net dipole moment will actually happen in this direction. Just don't really need the net. So that dipole moment would head in this direction. And what we know then, that means that the oxygen here would be more negative in water. The hydrogen side here would be more positive on this side. Yeah. And that's exactly what happens in this case. And that's actually technically how you're supposed to do it. You should stop it here probably. Kind of overshot a little bit. But we get a net sort of dipole moment happening in that direction. So you can see here with these two examples that you can have polar bonds in both. But when you have 3 or more atoms, the molecular geometry is really important to try to understand, you know, should it cancel out or should it not cancel out? In the case of CO2, because of the geometry, those individual bonds did cancel out, while in the water example, because of geometry, they actually added to each other and basically made a dipole moment heading in the upwards direction towards the oxygen. Any questions on that? So do we want to draw these things? Do we want to sort of visualize these things? There is sort of a very good way to figure out molecular polarity pretty quickly. And it does revolve around sort of your Lewis structure. And probably 98% of the time, you probably will be pretty accurate in your answer if you sort of follow what I'm about to tell you. Now, there's certain geometries which are referred to as being sort of symmetrical geometries. And there's certain geometries which are known as being unsymmetrical geometries. So typically symmetrical geometries happen when we have no non-bonding electrons involved and everything on the outside is the same. So maybe I have that chart here. So let's go back to that chart. That's probably way back here. It'd be easier maybe see in that chart, maybe. like watching the lecture backwards. It's good. I like it. In case you missed something, there it is. Maybe we could see it. All right, so if we look at sort of our chart here, and again, you have a similar chart in your book. If you look at sort of these molecular geometries and these charts, there's some symmetrical geometries. And typically, if you have a symmetrical geometry, you typically will have no non-bonding electrons on the center atom. And if everything attached is the same, it typically will be a non-polar molecule. So what are we sort of talking about here? Like trigonal planar, for example. Tetrahedral. Triangular. Bipyramidal, as I run out of room. Octahedral. Again, if you draw all these, so we'll take a look at this. So for example, here we can see that's our trigonal planar. This is our tetrahedral, right? Again, what they all sort of share in common is there's no non-bonding electrons on them, and it typically will lead to a non-polar molecule if everything attached is the same. So, for example, if we looked at, I'll just draw it like this, forget all the non-bonding electrons and all that, imagine they're there. If we look at all this, right, between carbon and chlorine, the chlorine is more electronegative. So again, this thing has basically polar bonds heading towards the chlorine. But the geometry here is tetrahedral, which is symmetrical. Everything attaches the same. So they're all going to pull in equal and opposite directions, and they're going to cancel each other out. And this guy would be a nonpolar molecule. So really, you could quickly look at that and go, I see my Lewis structure. I don't see any dots on the central atom. I see everything attached on the outside is the same. I'm a pretty safe bet that it's going to be nonpolar in that particular case, right? Now, if we take one of those guys, off, for example, and we put a hydrogen in its place, so we take something like this, we still have those polar bonds heading this way, heading this way, heading this way. Not accurate, not drawn in three-dimensional space. But now when we look at the carbon-hydrogen bond, that actually is a non-polar bond. So if you do the difference in electronegativity between carbon and hydrogen, the difference is 0.4. And even though it's technically non-polar, it is slightly heading in this direction, even though, again, it's typically non-polar. So what you essentially have in the case on the right is we have three guys kind of heading this way, and that fourth guy is like, I'm just going to go with you, basically. So they're all pushing in the same direction or pulling in the same direction. And it's going to go from a non-polar molecule to a polar molecule in that case. So that's sort of the rule there. The general rule is if you have one of these symmetrical geometries, which essentially means when you draw the Lewis structure, no dots on the central atom, everything on the outside is the exact same, you pretty much could do a safe bet and say that the molecule is going to be non-polar. But the exception to that is if you take out one of those guys on the outside and change it to a different element, it will typically go from being non-polar to polar in that case, because you will then have an overall difference. So that's sort of the general rule for symmetrical geometries. No dots on the central atom, everybody on the outside the same, non-polar. No dots on the central atom, everybody on the outside not the same, probably going to be polar. So those are sort of the quick way you could determine usually pretty accurately. Like anything else, there's probably some exceptions that pop up, but probably 9 times out of 10, or maybe even more than that out of 10, you'll probably get the right answer in terms of molecular polarity by thinking about it that way. Now, there's also, we'll use this side here maybe. There's unsymmetrical geometries. And unsymmetrical geometries typically will have non-bonding electrons. On the center atom. So what that essentially means is you draw the Lewis structure, you have dots on the central atom. And if you have that situation and everything is the same, so all the elements attached on the outside are the same, it typically will be a polar molecule, pretty much. So if you think about it, that's like your bent or V-shaped. That's your trigonal pyramid. That's your angular. You know, that is any of these, some other guys here. That's your seesaw, right? I see dots. Everything on the outside is the same, going to be polar. That's your T-shaped as well. You know, that has those type of situations. So I'm not going to list them all, obviously. And again, if we come over here, here's our angular, right? That would be polar. Our trigonal pyramid, I got dots, going to be polar. Our water has dots, going to be polar. So again, symmetrical geometries typically will have the dots on the central atom when you draw your Lewis structure. Everything on the outside will be the same, and it typically would be polar in that case. Now, there is really 2 exceptions to that sort of dots on the central atom. And there's the 2 exceptions. We could probably see it here if I didn't scribble over it. I don't think I did, so I think we're good. So the 2 exceptions for where you could have kind of dots on the central atom and the molecule actually be nonpolar. The first exception is actually right here. This linear, where you have 5 electron pairs and 2 bonds. And that is because what ends up happening in this situation, as you can see, if you draw the Lewis structure here, it has dots. But those dots are symmetrically equal to each other. Those non-bonding electrons make like a triangle, so they kind of cancel each other out. And then our bonding guys end up 180 degrees apart from each other, which means they also would cancel each other out. So the linear that is part of the expanded octet linear, not the regular linear, the 2 and 2, but the 5 and 2 linear, if you have that geometry and everything on the outside is the same, it's going to be a nonpolar molecule. So that's one exception where you can have dots on the central atom that it most likely going to be nonpolar if everything on the outside is the same. The other one is this guy down at the bottom here, is that square planar geometry. And that square planar is the 6 electron pairs and the 4 bonds. And that is because these 4 bonds make a square, which means as they each pull, they're pulling equal and opposite of each other. Again, if everything's the same on the outside. And those 2 non-bonding electron pairs are going to go as far away, equal and opposite of each other as they could get. So they will kind of cancel any type of contribution from them. But mainly the square part of it is very symmetrical. So those 2 that I just boxed there are really the 2 exceptions that most of the time will sort of fall in the symmetrical sort of deal where it will be nonpolar. And again, that is because of the symmetry that's there. And again, even though they do have those non-bonding electrons, they will still be very symmetrical. So that's the 2 real main exceptions that you should be aware of and that you'll come across. Those 2 geometries, even though they have dots, if they're still the same on the outside, it will be probably nonpolar. Any questions on that? So leaving us really one type of geometry that you truly have to sort of think about when you have it, and that actually is the original linear geometry, the 2 electron pairs and the 2 bonds, which is this geometry here. So when you have this geometry here, you do have to sort of visualize what's happening. And again, that one is pretty simple because it's just 3 in a row. You know, like we saw with CO2, right? They went an equal and opposite and they did cancel each other out. You could have them head at each other, which means they would cancel each other out. But it is possible with that geometry to end up with everybody heading in the same direction. And if everybody's heading in the same direction, then it would become polar. So the linear geometry of 2 electron pairs and 2 bonds is really the one that you sort of have to visualize. But the good news is because it's a straight line, it's pretty easy to determine, you know, are they going opposite of each other? Are they going towards each other? You know, you could probably pretty easily determine that. Any questions on that? Okay. So let us take a look. I think we got some examples, perhaps. Okay, and that's essentially what this slide was talking about, what we just talked about. Again, there's that unsymmetrical geometries or symmetrical geometries. And again, unsymmetrical geometries, for the most part, dots on the central atom, everything's the same on the outside except for those 2 we just talked about. And again, that's going to lead you to polar. And symmetrical geometries, everything the same on the outside, no dots, going to be nonpolar in most cases. All right. So here's an example, again, of the HCl, again, heading towards the chlorine being more electronegative, this being a diatomic molecule. Because that's the only bond that's present, we would have more electron density towards the chlorine side, less electron density towards the hydrogen side. That, again, means that this side of the molecule is more positive, this side over here is more negative. As a result of that unequal distribution of those electrons as a whole. Here's our CO2. Again, as we talked about, good example. It has a polar bond on each side, but again, because that geometry is linear, they're going to pull equal and opposite of each other and essentially cancel each other out. And as you can see here, again, usually red indicates a high area of electrons and blue not so much. So you can see sort of a mellow, even color all the way around, indicating that those electrons are really distributed as a whole, relatively equal over this molecule. Here's our water example that we talked about. Again, also has dipole, bond dipoles, and they do add to each other. And again, this guy in the middle would be our dipole moment. Indicating that this side of the molecule is more negative, this side is more positive, and you can see that here in sort of our electron density map. The top part where the oxygen is more red, which means more electrons. Bottom part more blue by the oxygens, meaning it's cooler, if you will, and not as many electrons heading out in that direction or that area. NH3. So if we look at NH3, again, if you draw the Lewis structure for NH3, pretty much all you have to do is look at it and go, I see dots. I see same thing attached all around. This is going to be polar. It's going to be a polar molecule. Pretty much all you have to do on that particular one there. And again, heading towards the nitrogen, and these non-bonding electrons going to kind of pull a little bit this way. And again, we get our net dipole moment heading towards the nitrogen, meaning in this case that the nitrogen part of the molecule is going to be more electronegative or more negative than the hydrogen part, which would be more positive. So why don't you take a look at some to see what you come up with. Let's see. Let's do this one. Actually, let's not do that one. Let's do the other one I was going to draw. I'll decide which one I want to draw here. Let's just do this one here. Go that way. Okay, so take a couple of minutes here, and for each of these, decide whether or not these guys are polar or non-polar, the molecule. And I'll do one more. Let's do this one. Okay, so let's take a look and see. All right, so let's start up here. If we look at this, again, if you want to kind of do it the quick way, I see dots on the central atom. I see everything attached on the outside is the same. This is our angular geometry, and this would be a polar molecule. When I look here, I'll make that H a little bit better. There you go. I do not see dots on the central atom, but when I look on the outside, everything on the outside is not the same. And remember that even though we don't see dots here, in order for it to be polar, everything on the outside does need to be the same element. So because it's not the same element, this is going to be a polar molecule. And again, the idea there is the carbon fluorine, they're going to be pulling towards the fluorine, all heading like on this side. This hydrogen is non-polar here, which means it's not going to resist it, which means these three guys are going to basically pull the whole thing, go that way, pull the whole thing that way. And you can kind of visualize, again, that movement happening. We come over here, I see dots on my central atom. Everything on the outside is the same. That's my bent or V shape. This is going to be a polar molecule. Here I see no dots on the central atom. I see everything on the outside is exactly the same. So that's going to lead me to it being symmetrical. And that means it's going to be a nonpolar molecule. Again, even though it has polar bonds between the sulfur and the fluorine, because those are technically equal and opposites of each other, all those bonds, they're going to cancel each other out. So again, that's the idea of pulling on the rope equally. There, even though you are pulling, you're not really going anywhere, right? So it's just kind of the same idea here, even though there's sort of a pull from each of the individual bonds, because they're equal and opposite of each other, it's going to be nonpolar. Coming down here, we have no dots. Everything on the outside is the same. It's going to be nonpolar. And in addition, besides that, what we see here is carbon-hydrogen bonds all the way around, which technically speaking means it has no polar bonds to begin with. Because remember, carbon-hydrogen is a non-polar bond. So really, technically speaking, in that guy, you don't even have polar bonds. You have all non-polar bonds, which should obviously lead you to a non-polar molecule. But if you miss that part, you could just still do it the same way we just did. Still no dots and everything attached is the same, so non-polar. But really, there's not even a polar bond in that particular molecule. Even though they're technically not in there being polar, still a little bit of polarity happening there. It is a little bit of equal difference separation between that. And again, what I mean is, technically speaking, as we talked about earlier, I think, the carbon-hydrogen bond is nonpolar because it has that difference of 0.4. But because there is still a difference and not a difference of 0, technically speaking, it is slightly going in that direction, but not considered polar to begin with. But in reality, there's still just a tad of pull heading towards the carbon, but not enough to make it considered a polar bond. Now, when we look at carbonate, just based on geometry for carbonate, I see when I look at my Lewis structure here, no dots, everything on the outside is the same, which means based on geometry, this should be a non-polar molecule. And some people might say, well, it has an overall charge, so it's kind of polar because of that. But just based strictly on geometry, this is trigonal planar geometry, which is a symmetrical geometry, which means all those oxygens should be equal and opposite of each other in a, badly drawn here, but a triangle sort of deal, right? Which means at each of those corners of the triangles, they're each pulling equally. And again, here, they're going to cancel each other out. Again, in CO2, there is polar bonds, right, between the carbon and the oxygen based on the difference in electronegativities. But because they're sort of in that triangle shape, they're going to be equal and oppositely pulling on each other and canceling each other out. Any question on any of those sort of examples? Now, molecular polarity does affect things like the solubility in water. So since water is polar, usually polar molecules and polar molecules are attracted to each other. And it's really because they have a way to interact with each other. And because they are polar, there's a positive side of the molecule and a negative side of the molecule, which means when you get two polar guys together, as we'll talk about in a later chapter, the positive side of one molecule is attracted to the negative side of the other molecule, allows them to mix really well. And that's why things that are very soluble in water are polar things, and also ionic things, which have positive and negative charges that interact well with the positive and negative side. That's also why non-polar and polar things really don't mix, and that's what we see here. Top layer is organic, which is basically non-polar, which is essentially neutral, has no charge. Bottom one is our water layer, which is polar. And again, water has that positive side, negative side. So when they try to interact with each other, they really have no way to interact with each other very well. And typically they will separate out from each other. So I think your question is on the SH2. So on the SH2, again, the geometry is like this, right? And in this particular case, again, it would be heading this way and this way. And as we talked about, those would add to each other, giving us, just like in water, actually that net dipole moment going that way. So if your question is about the non-bonding electrons, what happens with the non-bonding electrons here in this example is, let me try to find a spot where I could slap that. I'll drop it here. The non-bonding electrons in this guy, there's actually only 2 of them, which means they're going to go kind of like this, right? And in the one I think you're talking about where it was the linear exception, I think is the one you're talking about with the expanded octet. In that one, what you had with the non-bonding electrons, I'll just put the X here for the central atom. You had the non-bonding electrons kind of going this way. So they made almost like a triangle with themselves. And so any contribution from them sort of canceled each other out, as opposed to in this one here with SH, where there's only 2 of them. So kind of like if, you know, you had like a string that kind of came in like this. If you grab both ends of the string and kind of pulled it, right, the whole thing would go. But if you had like string that came in this way and one that came down, like a 3-way tug of war, if you will, and everybody pulled like on, you know, say the little flag was here and you had a rope going this way, a rope going this way, and a rope going that way, and everybody pulled on it, they're going to kind of cancel each other out, as opposed to, you know, if you had, you know, this sort of guy here and everybody sort of pulled on it, it would probably, the whole thing would move because everybody would be pulling in this direction, right? So that S would sort of move if you sort of think about it that way. So in the case of the expanded octet, there's that extra electron pair that kind of makes that triangle type of symmetry there. And in terms of the non-bonding electrons, that you don't have to worry about those in that case because they're pretty much equal and opposite each other, as opposed to SH2, you know, they're kind of just heading that way. Not really symmetrical in that case. And the other main difference as well is in that expanded octet, the bonding part of it, in addition to the non-bonding part, right? The bonding guys were linear to each other, right? So their net effect is like a straight line, and they also cancel each other out, which is why that expanded octet in that case would be non-polar. And that's different than what we have here with the SH2 because of the geometry here. You actually have the bonding guys really making it polar because they're going to add to each other, kind of just like in water. So you have those guys, because of their geometry of the bonding aspect of it being unsymmetrical, going to lead it to being polar. And the bonding in that expanded octet was a straight line. And again, pulling opposite sides of that straight line is also going to cancel each other out. So anywhere you look in that expanded guy, you got everybody kind of equal and opposite, both the bonding part of it and the non-bonding part with the electrons. They're all kind of equal and opposite and going to cancel each other out. Other questions on that? Okay. So this is sort of like soap, for example. Soap has a polar part and a non-polar part. And that's what makes soap really work, because dirt is non-polar. And the non-polar part of soap, which is kind of, I'll represent with these squiggle lines. These squiggle lines is like all these carbons and hydrogens. Really will trap the dirt because they mix really well together. And then on the outside, you have, you know, the charged part, the charged part like that, which is the polar side of soap. And that works really well because usually after we soap up, right, we get water and we wash it. And the water will mix with the polar side of soap, and the non-polar side will trap your dirt, and out it goes together with the water and stuff like that. So it works really well. So why don't you take a moment here, and for these two, decide whether or not these guys are polar molecules or non-polar molecules, and see what you come up with. And those are the electronegativity values on the left for each of the elements. Okay, so let's do this two ways. Let's just do our quick predictions, just based on what we talked about looking at the Lewis structure and trying to decide. So let's see here. I see dots on the central atom. I see everything attached is not the same here, and that probably is going to lead me to a polar molecule because of those dots. Now, when I look here, I don't see dots, but everything on the outside is the same. So probably going to be a nonpolar molecule. Again, with those dots on the central atom, most cases going to have that polar molecule happening. So let's kind of go through it and kind of see what we got going on. So first we want to see, do we have polar bonds here? So between nitrogen and oxygen, 3.5 and 3, if we subtract that, that's going to be 0.5, which means we do have a polar bond heading in this direction. Now, between the nitrogen and the chlorine, that is 3 and 3, which means technically speaking, that is nonpolar this way. So this nitrogen chlorine bond is nonpolar. The geometry of this thing is 1, 2, 3 electron pairs and 2 bonds. That is angular, which means technically if I draw it kind of like with the geometry here, kind of looks something like this. And in this particular case, what I have is only a bond heading in that direction, which means we would expect this thing basically to be polar, because you could kind of imagine in this case, I should draw, you have everything pulling down in this direction, right? So everything's just going to pull down from the oxygen side. And if you just think about just pulling from the oxygen side, you can kind of visualize the whole thing moving, and it should be a polar molecule in this particular case. Let's take a look at our sulfur and oxygen bond. Sulfur is 2.5, oxygen is 3.5. When we subtract that, that is 1 in terms of the difference, which means it is polar. So we would have polar bonds heading in this direction. So both have polar bonds. The geometry here, though, is 1, 2, 3 electron pairs, 3 bonds. That's your trigonal planar geometry, which means technically speaking, let's sort of draw it ish, it's going to set up that triangle type of thing where this guy is pulling this way, this one is pulling this way, and this one is pulling this way. And again, as I was just mentioning in that previous example, they're all going to be pulling equal and opposite of each other, which means this guy also, like we predicted, should be a nonpolar molecule. Any questions on that? I think we have a much better, no, maybe we don't have a better picture of that. No. Any questions on that particular thing? So guy on the right should be nonpolar because of the symmetrical geometry, even though, again, it has polar bonds. The guy on the left there will be polar because, again, you could just visualize pulling just the oxygen, right? And nothing else is pulling on it. So you could kind of visualize the whole molecule probably moving, while, again, on the guy on the right, everybody's pulling equal and opposite of each other. Any questions on molecular polarity? This one we sort of talked about anyways, so I think that's good. Oops. Any questions on that? Okay, so that wraps up chapter 4, and that should wrap up lecture, I think, too. So we'll start lab. Start lab at 9:50 or so. So about 9:50 we'll start lab. And again, we're not going to do experiment 7 today. So we will start experiment 7, I think, tomorrow. I think it's experiment 7. So today I think we'll just be sort of, you could continue working on your study assignment. You can continue working on your lab report if you need to. And if you have questions, I'll be happy to answer them. But I think that's pretty much what we're going to kind of do in lab today. So just show up there at the beginning. We'll talk a little bit, and then obviously you can continue working on. Any questions on anything? Okay. I will see everybody in about 20 minutes. Go stretch.